Hi science friends. Today we're going to be talking about the two-factor cross. So we're going to do two examples of a two-factor cross, and then you have the worksheet from yesterday to finish up. You'll have the two-factor crosses there at the bottom, and then also I'll talk just a tiny bit about chi-square at the end, and you have those chi-square problems to do, two chi-square problems to do as well. So make sure you're using the chi-square problems I gave you yesterday, not the ones that were previously in your binder, okay? So two-factor crosses. Let's look at this first one. It says about 70% of Americans perceive a bitter taste from the chemical phenolphthalein, or PTC. So if we were in class, we would actually taste this. We will do it when we come back, so y'all just remind me. The ability to taste the chemical is a result from the dominant allele, big T. So I'm going to make a note that the big T is a taster, okay? That means that the little t is a non-taster, okay? And it goes on to say that, and not being able to taste PTC is a result of having two recessive alleles, little t, okay? So today we're talking about two-factor crosses. Everything we did yesterday was just one factor. We're looking at coat color or plant color or height or whatever. In a two-factor cross, you're looking at two different traits simultaneously. So this one is about PTC tasting and albinism. Okay, let's keep going. Albinism is also a single locus. Remember that word locus, not locust, Alex. But locus is a specific spot, a specific location of a gene on a DNA or on a chromosome. A single locus trait with normal pigment being dominant. Okay, so big A is going to be normal pigment. And so that means little a is going to be albinism. Oops. I don't know what's happening. You get the drift, okay? A normally pigmented woman, so if she's normally pigmented, we know that she has to have at least one big A, who is heterozygous for PTC tasting. So she's going to be heterozygous. She's going to be big T, little t. Has a father who is homozygous for both albinism, so that means her dad is albino, so he has a little a, so he must give her a little a. Her dad is homozygous for albinism. If he's little a, she's going to get one of these alleles from each parent. So that means that little a allele had to come from her dad, because that's all he has to give. Her mom must have given her the big A. He's also homozygous for PTC tasting, so he must have given her the big T, since he is a big T taster. All right, so here's our woman's genotype. Let's circle that. She marries a man, a heterozygous, normally pigmented man. So if he's heterozygous, normally pigmented, he's going to be big A, little a, who is a taster. So we know he has to have one big T for tasting, but who has a mother that does not taste. So if his mother is a non-taster, that means she's little t, she's going to have to donate that little t to him. He must have got the big T for tasting from his dad. Okay? So this is his phenotype. So basically our boy and our girl are both big A, big T, little t. And so we need to do a two-factor cross for this. I'm going to open up another tab, so I've got a little space here. So I'm going to do big A, big T, little t, times big A, big T, little t. Okay? And then I'm going to make my Punnett square box. Now this one's going to be significantly larger. It is a 4x4 square, so it's going to have 4 rows and 4 columns. Now, the trickiest, hardest part of this, not that it's hard, but it's, if you forget something on how to do it, it's this part. It's how to get what goes above these spots, and then also on the sides, okay? So the way you do that is you use the FOIL method, just like you FOIL in math. Remember, first, outer, inner, last. So we're gonna FOIL this one and get us the top or the side, it doesn't matter which one goes where, and then FOIL the other one and get the other top or side, okay? So first is going to be big A, big T. And again, these don't really matter what order you go in, but if you use foil, you'll know that you've done it correctly. Big A, big T. Outer is going to be big A, little t. Inner is going to be little a, little t. I'm sorry, little a, big T, excuse me. And then last is going to be little a, little t. Okay? Basically what I'm doing here is giving all of the possible combinations of the gametes. Okay? They could get the big A for albinism. They could get the little a for albinism. They could get the big T. They could get the little t. And so we're looking at all of the combinations of that. And so foiling that is the way to go. And then we're going to do the other parent on the side. Now, because they are the same, I'm just going to copy what I already have down there, because if I foil them the same thing, I'm going to get the same thing. Okay? So then I'm going to fill in my Punnett square. I want to always, this is important, put the A's beside each other and the T's beside each other. Okay? Try not to make any mistakes here as you do that, like I almost did. And just to make sure we know what we're doing, we're bringing the one on the side, big A, with the one at the top, little a, the one on the side, little t, and the one at the top, big T. Typically, you would want to always write the big one first. Big A, little a, big T, big T. But if you do it the other way, it's not really wrong. It's just a little easier to read them if you write it first, the big one first. And this does take just a little bit of time, as you see. Hopefully I don't make any more mistakes. Okay. So then I think the question asks to give the genotypic and phenotypic ratios of the offspring. I haven't actually crossed out genotypic ratios. I mean, you can do that pretty easily. I have full confidence that you can do that. But what I want to really talk about right now is the phenotypic ratios, okay? So, the possible phenotypes that you could have from this cross, let's talk about this one first. So this one would be normal skin, and they would be a taster. So let's try to find all of the other ones that are normal tasters. They must have one big A and they must have one big T to be a normal taster. So there's one, here's another, here's another. I'm going to circle them all. They have one big A and one big T. They'll be a normal taster. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 9 out of 16. If you wanted to convert it to a percent, you could calculate that out. Let me see what it is. It doesn't really matter, but 56.2.3. Okay. I'm not going to focus on the percents right now, though. But 9 out of 16. All right. Now, we could also, let's look at this guy. He's a normal non-taster. So let's look for those. They must have one big A, and they must have at least one big A, and they must have 2 little t's. So let's do them in a different color. Okay, so 1 big A and 2 little t's. 1 big A and 2 little t's. So I think that's all of them. They're going to be 3 out of 16. Okay. Let's change our colors again. Now let's look for ones that are albino and a taster. Okay. So to be albino, they have to have 2 little A's. And to be a taster, they have to have at least 1 big T. So So there's 2 little a's and 1 big T, 2 little a's and 1 big T, 2 little a's and at least 1 big T. So again, that gives us 3 out of 16, okay? And then there's one little guy left here, and he is going to be an albino non-taster. Little a, little a, little t, little t. And so what we see here, go back to a different color pen that we can read better than yellow. You get a 9 to 3 to 3 to 1, 9 to 3 to 3 to 1 ratio. This ratio is very, very important, okay? This is the biggest, longest Punnett square that you would routinely be asked to do, that you would be asked to do on like an AP exam. And it took us a few minutes to do it. I don't know how this video is going down, but I'd say we've been working on it for 6 or 7 minutes. Granted, I've been explaining through it, but it took us a minute. But if you know the 9 to 3 to 3 to 1 ratio, you don't even have to work the Punnett square, okay? Anytime you take 2 parents that are heterozygous for both traits, you will always get that 9 to 3 to 3 to 1 ratio, okay? They have to both be heterozygous for both traits. Now, the 9 is always going to be 2 dominant traits. Being a normal skin color and being able to taste PTC, those were both dominant traits. The 3s are going to have a dominant trait paired with a recessive trait, okay? Normal skin and a non-taster, taster and an albino. A dominant trait and a recessive trait are going to be your 3s, okay? And then the 1 is going to be both recessive traits, all right? So if I gave you an example, let's say your chi-square uses this one, okay? This is where chi-square is going to come in. Let's say you took a poll of 800 people and, no, let's not use 800. Let's say you had 8 fruit flies, a pair of fruit flies that are heterozygous for both traits. We use fruit flies a lot to study in genetics. And this pair of fruit flies gave rise to 800 offspring. I don't even know if that's legitimate. We're going to go for it, okay? And then it wants to know, it gave you how many of them had these certain traits, okay? In a chi-square, remember you have to compare observed and expected. So you would have to be given your expected values. Given your observed values. Your expected values are going to come from your Punnett square. So you would have to work out a Punnett square to know that, all right? If you just know 9 to 3 to 3 to 1, you don't have to work out the Punnett square because you know what those ratios should be. You would multiply 800 times 56.3% and see how many of them should have that trait. You would multiply 800 times 3 out of 16 since there's 800 offspring and see how many should have that trait, and so on and so forth. And then you could use those as your expected values and do observed minus expected squared over expected, sum those up to get your chi-square and compare to the critical value, okay? Make sure in your explanations you use that term critical value, okay? I want you all to get used to using that term. The critical value is what you're comparing to in the probability table. Y'all are pretty good with using the term degree of freedom, but I want you to use the term critical value. That's the number you read when you look at probability of 0.05 and then whatever your degrees of freedom are, okay? In a question like this, how many degrees of freedom would we have? We would have 3 degrees of freedom because there's 4 options. Your offspring could be one of 4 things, okay? So there's 4 categories, and then remember degrees of freedom is number of categories minus 1. So your degrees of freedom in a question like this would be 3. So make sure to incorporate that information as you go to do chi-square. If you get stuck on those, holler out at me. All right. Now, I think there's one more question for us to address. Let's look at this last one. It says a blue-eyed left-handed woman marries a brown-eyed, right-handed man who is heterozygous for both traits. So the man is, it doesn't tell us, let's use eyes. He's heterozygous for eyes and heterozygous for hands, okay? Now, our man is right-handed and brown-eyed. So that's going to tell us that Big E is brown eyes and Big H is right-handed, okay? If he has brown eyes and right hands and he's Big E little e and Big H little h heterozygous, then we know that the dominant trait is brown and the dominant trait is right, okay? So our woman then, it says she is blue eyes and left-handed. So she would be little e, little h, okay? So let's do a Punnett square for these guys. See what their babies are gonna look like. Big E, Big H, little h, times little e, little h, little h. Okay, so we're going to do our FOIL method first. Outer, inner, last. And then the same over here. First, outer, inner, last. Oops. That one's pretty easy to tell because that parent is only going to have little e's and little h's to give. See how it's all the combinations, and all of their combinations are the same because that's all that that mother has to give. Okay? So, let's fill out our Punnett square. Now, we could keep going and filling out the rest of our Punnett square. But because all three of these rows are the same as this row, all of those are going to be the same. Okay? So it's not important to me that you fill it out because I just want to know that you know how to find it and that you can give me like the phenotypic and the genotypic ratios. All right? So our genotypic ratios, I don't know what it asks for. Phenotypic and genotypic ratios. Okay? So our genotypic ratios, we're going to have 25% Big E, Big H, little h. 25% Big E, little h, little h. 25% little e, Big H, little h. And then lastly, 25% that. So just taking those from this Punnett square up here. There's one of each of them, so that's what our ratios are going to be, okay? We could use those to predict ratios in a chi-square, expected outcomes, all right? Now, what about the phenotypic ratios, okay? Well, this one and this one okay, so we're going to have, this one's going to be brown eyes and right-handed. This one's going to be brown eyes and left-handed. This one's going to be blue eyes and right-handed. And this one's going to be blue eyes and left-handed. Okay? So the phenotypic ratios are also going to be the same. Okay? So 25% brown and right, 25% brown and left, 25% blue and right, and 25% blue and left. Okay? So if you have any questions on these and these two-factor crosses, then let me know. If not, then finish up the rest of that worksheet with the two-factor crosses. You can just turn those in on Monday and finish up the chi-square and holler if you need me. Y'all have a great day and a great weekend. Go play in the snow.